Hello and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be doing the Fourier series of the periodic impulse train, where this to the left is the depiction of the graph and this to the right is the function of the periodic impulse train. And we're going to take the period t to equals to 2 and a to equals to 2 as well. If you want to go ahead and pause the video and see if you can figure out the Fourier series of this impulse train, feel free to do so and then come back to the video and see if you got the right answer. So from a previous video that I made labeled the Fourier series part 1, we noticed that we can reconstruct any periodic symbol x of t by the sum as k goes from -infinity to infinity. This sequence coefficient ck times this complex exponential e to the j k omega naught t, where again ck is simply 1 over the period t integrated over one singular period x of t e to the minus j k omega naught t dt. If you need a refresher on this, I have posted the link in the top right hand side corner of this video, so please feel free to check that out. Okay, before we go in and solve for x of t and ck, we want to notice that although the period is given here, we want to see it pictorially. So we see that at minus t over 2 to t over 2, this is a single period because it repeats itself, right? So we can say here from t over 2 to, let's say, 3t over 2. Again, it's a repetition, and that repetition is a times the Dirac delta function. Okay, so in this screen, what I've done was I've written out my x of t and my coefficient ck, and I've substituted my periods from -t over 2 to t over 2. In order to solve for ck and x of t, we want to note two properties. The first being what's called the shifting property. All right, and the other being the equivalent property. Okay. And essentially, I'm not going to dive into too much details about the proof behind these properties, but I'm just going to state them, essentially because the purpose of the video is to solve the periodic impulse train. So the first thing I want to notice about the shifting property is that the integral from -infinity to infinity of this Dirac delta function, or delta t minus t naught dt, is equals to 1. If we go ahead and multiply this by a constant, so the integral from -infinity to infinity x of t naught, so again a function x of t, but just at a specific point t naught, times delta t minus t naught dt, this is simply equated to the constant x of t naught. And the last thing the shifting property tells us is that the integral from -infinity to infinity of x of t times the Dirac delta function, delta t minus t naught dt, is also equated to t of t naught, because the only important factor of x of t is this value, x of t naught. The last thing we want to notice is that equation number 2 here, let me call this 1, and equation number 3 are both equal to each other. So we can say then that these two are the same. So essentially, the equivalent property says that x of t naught delta t minus t naught is equated to x of t delta t minus t naught. Okay, so we're going to use these two properties to solve for ck and eventually solve for x of t. So in order to solve for ck, what I'm going to do is I'm going to rewrite ck as the following. 1 over t integrated from negative t over 2 to t over 2. X of t is this a delta t minus t naught, where again, this t naught, if you scroll up, is basically 0. But nonetheless, we can still write it as t naught. So it looks like this function here. And then we can multiply that by e to the negative jk omega naught t times dt. So we notice two things. This here, again, is my function delta t minus t naught located here. And this here is actually my x of t. All right, so let me go ahead and rewrite this on a clean page. Okay, so I just went ahead and rewrote the CK equation. And we need to notice that again, this here is that still that delta t minus t naught. And this here is x of t. If this is confusing, please leave a comment down in the comment section below and I'll be sure to get back to you. But essentially, we can go ahead and say that CK is equals to A over T. I just went ahead and pulled this A outside times X of T0, where X of T0, so this is A over T, X of T0 is simply e to the minus j k omega T0. So we know that T0 is 0, right? Because here, this is 0. So then this basically becomes A of T. So then we can go ahead and solve for X of T. And we get that, therefore, X of T is equated to the sum as K is equals to negative infinity to infinity. A of T e to the j k omega naught T. If we take then that t is equals to 2 and a is also equals to 2, this means that omega naught is equals to 2 pi over t, or simply 2 pi over 2, or simply just pi. So therefore our final equation will be x of t is equated to, this here is simply just 1. All right, so we can go ahead and write the 1, or we could omit it and say then that this is just the sum as k is equals to negative infinity to infinity e to the j k pi t. And this is what we consider to be the Fourier series of the periodic impulse train in the complex exponential form. All right, so this is our solution. Let's go ahead and box that. So now we want to go ahead and write this in the real form so that we can draw a Desmos graph of it and visualize it in real time. So in order to do that, we want to go ahead and write out x of t using sines and cosines. So this is going to be x of t is equated to the sum as k is equals to negative infinity to infinity of cosine pi kt plus j sine pi kt, close parentheses. If we go ahead and split out this summation, we're gonna get that this is equals to, from negative infinity to negative 1, we're gonna get that we have a cosine of pi negative k, right, t, plus j sine, this is going to be pi negative k t. Okay, so that's the negative values. For k is equals to 0, sine, this here goes to essentially 0, and this here goes to 1. So we're going to get a plus 1. And then for k is equals to positive k, we're going to get a cosine pi kt plus j sine of pi kt. And essentially, what we want to note is the following. So we want to note some trig rules saying that cosine of negative x is equals to cosine of x, and sine of negative x is equals to minus sine of x. As a result, we can make this a positive, and this stays as a positive. If we make this a positive, this goes to a negative. And as a result of that, this term cancels out with this term, and we just get 1 plus my cosines. So the final solution is we can say then that x of t is equals to, we have this 1 plus, again, the 1 is coming from here, plus the summation of k is equals to 1 to infinity of 2 cosine pi kt. And this here is my Fourier series of the periodic impulse train using real terms. Let's go ahead and graph this in Desmos so we can see how it's behaving. So if we go ahead and come to Desmos, we can type out y of t is equals to, so it's 1 plus the sum, as let's be consistent, k is equals to 1 to, let's just say 5, so it doesn't take too long to render. So this is 2 cosine n or pi kt. As you can see, we're getting an impulse, right? Again, the reason why it's ending at 11 is because this has to equate to an area of around 2, because a was 2, all right? And again, we're getting periodics at 0, 2, 4, 6, 8, and -2, -4. If we go ahead and we increase this, let's just say to something like 20, you'll see that this is becoming more and more like the impulse, all right? Like the periodic impulse train is shooting more and more up to infinity. And if you shoot this all the way up to infinity, it will be a nice clean signal like our periodic impulse train. The only reason why I don't want to do it in this video is because it's going to take forever to render, all right? Because you need a lot of processing power to even change this to, let's say, 1,000. But for now, let's just keep it at, let's just say 10. And we could see a really nice periodic impulse train. I hope you liked the video. If you have any questions, please leave them down in the comment section below, and I'll be sure to get back to you. Please share the video and please subscribe to the YouTube channel. It really helps the algorithm. Thank you.